Okay, so we are going to be working through Chapter 9, Power. A note here, we have no new packages. You don't need to change your setup script or anything. We're just listing here the packages you need at a minimum to do this lesson. So I'm going to find my R project. We're in ESS 523A, Fall 25. Make this. Close out of all these. Okay, and I'm going to create a new R markdown to work through today. Oops. I'll make it bigger. There we go. Okay, so first things first, we run our setup script. Great, we've got all of our packages in there. Okay, so we have some recommended pre-work / review. We have this video on statistical power. We did not make this. I think we just thought it was a good, kind of fun. It's kind of a funky video.
It's weird.
It's a bit weird. But good explanation of statistical power. And then we've also, since we're kind of wrapping up statistics this week, have this little review box for you to review. We've written the null hypotheses of each statistical test we've learned so far. So remember, this is the null hypothesis. If we run this test and we get a significant p-value, something less than 0.05 is what our arbitrary cutoff value is, then you reject this null and accept the alternative. So just a note to review those things this week. So today we're talking about power, and we're going to use some of the coding wrangling skills we've learned so far to explore power's impact on statistical results. Power is essentially a measure of how effective a statistical test is at finding the true trends or effects or patterns in your data. And power is influenced by sample size, such that larger samples provide more power. This is something we've been talking about so far quite a bit. And also effect size. When there's larger or more dramatic effects or dramatic differences, those are easier to detect. So these are the two things when we have larger sample sizes and larger effect sizes. That's having more power. That is giving you more confidence in your statistical findings, that you are finding the true patterns. Okay, so let's explore power in action. For today's lesson, we are going to test power by we're going back to our penguins data set, and we're going to compare the bill length across our Gentoo and Adelie species. So let's load in and filter data. So a reminder, if this is still confusing, when we use this data function, this is how we call in data sets that already exist in an R package. In this case, the penguins data exists in the Palmer penguin package. However, when we've been reading in data from a file on our computer, that is when we use read CSV. So just a reminder on the two different ways we can read in data depends on where the data is stored. So we want to read in penguins, and then, here we're going to keep just the Adelie and Gentoo species. We're going to drop the third. And then just a note here that t-tests don't like factors, and so this line of code is just converting our species column to a character. And then let's perform a t-test. And throughout this lesson and your homework, we're just going to stick with the non-parametric t-test by setting var.equal = false. So we don't have to keep testing for if we meet the model assumptions. So penguins, filter, species statistical open. And if you don't want to worry about spelling, you can just copy and paste this from the lesson plan too. I will probably mess this up. And then we want to mutate our column. And then do our t-test. Make sure I'm doing this right. Yeah. And so for this test, we're looking at if bill length differs by species. We're going to set var equal to false. What was the other thing? Detailed equals true to see the full results. Okay. So this is the results of our raw penguins data set looking at does bill length differ between Gentoo and Adelie. We see we have it didn't print the p-value for me. If that happened to you, I'm going to add this. Oops. Okay. And a reminder, I think we've used this maybe randomly here and there, but if you feed your output into capital V view, we use this a lot when, for example, we can't see all of the results printed in the console. If you thread it into view, it'll open those results in a tab like this. So this will let me see all of the columns in the data. So this is a pretty small, very small p-value. So we find pretty significant differences between our Adelie and Gentoo penguins in terms of their bill length, where Gentoo have much bigger bill lengths than the Adelie species. But here we have sample sizes in the hundreds, about 150 of each species. So what we're going to do next is first test out how sample size affects power. So let's say, for example, we're going to use this slice sample that we've used previously to pull out a random sample of, let's say we only had 2 penguins of each species. And to pull out 2 per species, we're going to add group by, and then I'm also going to drop NA so that it doesn't accidentally pull out an NA value when we choose the random rows. And then we need to, I don't know if we've done ungroup yet, but often since we're piping a series of code into, in this case, a statistical test, it doesn't operate well on grouped data. And so there's often cases like this where we just need to add ungroup to remove that grouping term and then feed it into t-test. So I'm actually just going to keep building on this existing coding chunk, but you can create one for each part of the lesson like it does in the website if you want. So we forgot what I'm doing already. Okay, we got to drop NA and group by. Drop NAs for bill length. Group by species. And then slice sample. And we're going to choose N equals 2. So this will pull a random 2 Gentoo penguins and 2 Adelie penguins. And then don't forget to ungroup. And then feed it into our t-test. And I'm going to keep view up here just to make sure I can always view the full results. Let's move this down a little bit. Okay, so now when we run this, now every single person in this room will probably have different results here because each of us is pulling a random subset of 2. And therefore, those will have different values of bill length, and these statistics will likely be different. But now we see, remember that really, really small p-value is now quite large, 0.15. This is actually a not significant p-value. So therefore, when power is much smaller in terms of sample size, we have much fewer samples, our findings are actually not significant. We did not have enough power to find significant differences in these 2 penguin species. So case study number 1 of power in action. That's looking at sample size. Now let's look at the second element that affects power, which is effect size. First, we are going to look at the distribution of our bill length in each species. I'm going to copy this. Okay, so this was looking at sample size. I'm going to create a new section for effect size. Okay, I'm going to copy and paste that ggplot code because I know I will have a typo. And a new thing we're adding here is this geom, V line. This is adding a vertical line at whatever x-intercept value you give it. And what I want to do here, as shown in the lesson plan, is I want a line at the mean of each group. And so I actually pulled the mean of the Adeli and the mean of the Gentoo from when we previously ran the original t-test, and it prints out the means of each group. That's where I got it. So I just got these numbers ahead of time. You aren't supposed to know these magically off the top of your head. When we run this, we see the chart that looks in the lesson plan. So these means are different, where again we see the Gentoo looks larger than the Adeli, but there's a lot of overlap between these two species, where if we actually set alpha, oh, that's not working as well. Oh, it's because of the type of bar chart we did. Anyways, there's a lot of overlap. And so to test effect size, we're just going to pretend that magically overnight, all of the Gentoo penguins grew 15 millimeters in bill size. Don't know why, just happened. And so I'm going to add this line of code here, which is mutating the data to reflect that magical phenomenon. And so we're going to create new values for our original bill length column, where for all of the Gentoo species, we're going to add 15 millimeters to bill length. Otherwise, the Adeli, they're going to stay at their original bill length. Close out of that. Okay, so let's add mutate bill length millimeters. Use if else. Oh no, if species equals Gentoo, we're going to add 15. Otherwise, keep the original bill length value. And then I also, now, again, I found this value separately on my own investigation. The mean of the Gentoo is now 62.5. So I'm just editing I'm editing that V line to reflect the new magical mean bill length of the Gentoo penguins. So now with our magical species, if we recreate that same chart, we now see a much bigger divergence in bill size. This is a stronger effect size. The effect of whatever elements are affecting these species' bill lengths is much stronger. It's a bigger difference. This will give us more power in our statistical findings. Okay, so now let's redo the t-test. Again, I'm just going to override this part. So with that new magical data set, we're doing the same t-test that we did at the beginning of the lesson. And I'm going to add the view in here again. So now, oops, what did I do? I think it's because Yep, I didn't mutate. This is the error it throws, I think, when trying to, I didn't convert the species to a character. Now it should work. Yep, it doesn't like factors. Okay, so remember the p-value before was like e to the negative 69? Now it's e to the negative 159, which is like way, way, way bigger. Actually way, way, way smaller. And so this is showing that we have a reminder of what this p-value signifies. This is the probability that the difference you are seeing in your data happened by chance. So now that we have this much stronger effect size, much stronger difference between our penguins because of the magical wizard that grew their big bill lengths, there's a much, much, much teeny tiny percentage that this happened by chance. Okay, now let's try combining the two. Let's keep our magical Gen 2 big-billed species, but now let's redo the t-test with our smaller sample size. Let's see if our bigger effect size actually gives us more confidence with our smaller sample size. Let's see, so I'm going to here group by our species and then slice sample 2. Remember, got to ungroup again. And then do the same t-test. Let's see. Again, your answers may vary. But in my case, ooh, almost. Still not significant, though. But in my case, when I did the t-test of the smaller sample size with the bigger effect size, that bigger effect size still, again, depending on what random rows it chose, still gave me a smaller p-value than before, but in this case, it's still not as significant. So sample size is still pretty important. 2 penguins, you would probably never feel good about doing a statistical test when you have a sample size of 2. But this is just for demonstration purposes. Okay, so that is today's lesson. We have this little note here about random selection. What I've been saying before is that depending on what random rows you chose, everyone's results may be different. The assignment. For this week's assignment, we are going to do similar to what we just did in the lesson plan with penguins and bill length. But we're going to go back to our trout data and look at difference in weight in clear-cut trout, or in cutthroat trout, between our forest section, between the clear-cut and the old growth. So this is the same t-test we did in our t-test and ANOVA lesson. But now we want to do that same t-test, but by exploring our how our differences in sample size will affect those t-test results. And so we're back to our original question. Biologically, we want to test for, is there a significant difference in trout weight between those that were found in the old growth forest versus the clear-cut forest? And so we have this section here to set up your assignment. We're using the Anvertebrates data from the LTR data sampler package, and we're going to filter out the cutthroat trout species and drop any NA values for weight. So this trout data is what we're going to be using downstream in the assignment. So the assignment is 4 questions, and overall, what we want to do is we want to run this t-test, but at 4 different sample sizes. We want to run it at a sample size of 5, a sample size of 10, 1,000, and 5,000. And we want to, by the end of this assignment, you'll see how sample size affects your p-values. The histogram in question 4 is pretty cool. It's like, whoa, it's important. So question 1, this may be the hardest one because it is asking you to write your own function. So we're just telling you to create a new function called trout subber. You can call it whatever you want. This is just the name we thought would be appropriate. And what this function will do is take a user selected number of observations, the thing that is changing, from our trout data frame above. So we want a function that will pull out any sample size we give it. So essentially, we think about functions, we can apply them over and over again, but the thing that is changing is the sample size. Because again, we want to do this for a sample size of 5, 10, 1,000, 5,000. And so what we did here is we helped you a bit. We wrote out the code that you would do for one iteration. And so using this template code, you'll turn this into a function where, hint, hint, the thing that is changing is this slice sample where you're changing the n value. Okay? So that's number 1, is creating a function that you can use to slice a sample of any value of n. And then number 2 is building on that function by adding in, at the end. Am I reading this right? Didn't we already do that in the example?
Mm-mm. Well, we gave them the code to do both at the top.
Okay.
They're creating 2 different functions. They're building off of the first one. It's really easy.
Okay.
It's really easy.
And then, yes, this template code helps you with numbers 1 and 2. And then 3 is where we're going to use map. And this one is a little tricky too. So if we think about map, it takes in the first argument is a vector of some thing, where each element in that vector is going to be the argument in a function you give it. And what we want to do is, because slice sample is a random selection, for each sample size, so we have 4 sample sizes, we want you to run the t-test 100 times each, so we can account for some of that randomness. And we have a hint here that, think about, so we currently have this vector of 4 numbers. We want to repeat each number 100 times. So we're going to make use of the rep function to create the vector that goes into the first argument of map. And then we have a hint here too that the output for question 3 should be a single data frame with 400 rows, because one iteration will output a single line of your t-test results like this. And since we want to do 100 iterations of each of the 4 sample sizes, there will be 400 rows in this final data frame. And then question 4 is, using that output data frame with the 400 rows, is to make a histogram of the p-values. So this will show us, and then we want to facet by our sample size. So if you think about this, output should be a 4-paneled figure, each showing the histogram of p-values for each sample size. And that's where you'll be like, wow, because it'll really show you how powerful a sample size is. Okay, going to end the recording.